Welcome to a powerful new module, Threads. Up until now, our code has executed sequentially one instruction after the other. But modern applications must handle multiple tasks simultaneously, like responding to a user interface while downloading a file in the background. This concurrency is achieved through threads. 1. Process versus thread. To understand a thread, you must first know a process. A process is an independent instance of a running program, such as your Python interpreter or a web browser. Processes are isolated. They do not share memory. A thread is the smallest unit of execution within a process. Multiple threads within the same process share the same memory and resources, making communication and coordination much faster. 2. What is multithreading? Multithreading is the ability of a single program to manage and execute multiple threads concurrently. This concurrency is crucial for tasks where one part of the program is waiting for an external operation to complete, like network input or disk access. While one thread waits, the operating system may switch control to another thread, keeping the CPU busy and the application responsive. 3. The Python threading module. Python provides the threading module to create and manage threads. We will use the main thread class from this module, along with methods like .start parenthesis to kick off the thread's execution. We will also explore functions to identify which thread is currently running the code, which may be useful for debugging. To summarize, threads enable concurrency by sharing resources within a single process. Our next lecture 26.02, Main Thread. See you there. Welcome back. Every Python script you have ever executed has run within a thread. When a Python program starts, the operating system creates a process, and that process automatically creates one default thread to execute your code. This is called the main thread. 1. Role of the main thread. The main thread is responsible for executing all sequential code in your script. It is also the thread that, when it completes its execution, signals the operating system that the Python program should shut down. All user-created threads run concurrently with and are managed by this main thread. 2. Identifying the current thread. To verify the existence and identity of the main thread, we use threading.currentThread parenthesis. This function returns a reference to the thread object that is currently running the code. We may then access its .name attribute. For the default thread running your script, this name is always main thread, and its daemon status is always false. 3. The execution flow. Any line of code you write outside a function or a custom thread is executed sequentially by the main thread. From the first line to the last, the entire script runs under the main thread identity. We will use this knowledge as a baseline when we start creating new threads in the next section to clearly distinguish between the default execution flow and the concurrent flow. To summarize, all Python code runs in the main thread. Our next lecture 26.03, Thread using a function. See you there. Welcome back. I have a way to create a new thread in Python is to pass a target function to the threading.thread class constructor. The new thread's job will be to execute that function concurrently with the main program. 1. Defining the thread's task. First, we define a regular function, here named task function, which represents the independent work we want to run concurrently. Inside this function, we identify the thread executing it, which, for a new thread, will not be the main thread. This function will be the entry point for our new thread. 2. Creating and starting the thread. To create the thread, we instantiate threading.thread. We must pass our task function to the target argument. If the function accepts arguments, we pass them as a tuple to the args argument. Notice the comma after the single string argument to ensure Python recognizes it as a tuple. Importantly, creating the thread does not start it. You must explicitly call newThread.start parenthesis to instruct the operating system to begin executing the target function in a new, concurrent thread. 3. Execution order or concurrency. The key takeaway here is that once .start parenthesis is called, the main thread immediately continues to the next line of code. It does not wait for the task function to finish. The task function now executes concurrently, meaning its output may interleave with or appear after the main thread's output. This is the essence of multithreading. To summarize, creating a thread from a function is simple using, target, and args. Our next lecture 26.04, Printing Thread Names. See you there. Welcome back. When debugging or logging a multi-threaded application, knowing which thread executed a specific piece of code is essential. Python automatically names new threads, but using descriptive, custom names makes tracking concurrency much easier. This section focuses on naming threads. 1. Default thread naming. When you create new threads without specifying a name, the threading module assigns a default name sequentially, thread-1, thread-2, and so on. This mechanism helps distinguish them from the main thread, but these generic names are not very informative about the thread's actual purpose. 2. Assigning custom names. To assign a meaningful name, you simply pass the desired string to the name argument in the thread constructor. Here, we create one thread explicitly named downloader thread and another named data processor. When these threads run the worker function, the output will clearly indicate which thread is performing the task, greatly simplifying debugging. 3. Retrieving the name, which is a practice. To access the thread's name inside the function it is running, you must use threading.currentThread.name. This practice ensures that all logging and error messages automatically contain the context of which thread generated them, which is absolutely vital in multi-threaded programming. To summarize, always name your threads for clarity. Our next lecture 26.05, Thread Extending the Thread Class. See you there. Welcome back. While passing a function to the target argument works well for simple tasks, the object-oriented approach is often cleaner for complex threads that need to maintain internal state or properties. This involves creating a custom class that extends the base threading.thread class. 1. Defining the custom thread class. To extend the class, we define class workerThread, parenthesis, inheriting from threading.thread. Crucially, we must override the special .run parenthesis method. This .run parenthesis method is the equivalent of the target function. When the thread starts, this is the method that executes. Any initialization, like setting the thread name or internal data, is done in the constructor, remembering to always call the parent's constructor using super.init parenthesis. 2. Instantiating and starting the class thread. To run the custom thread, the steps are familiar. First, instantiate the class just like any other Python object, passing any arguments defined in your custom constructor like the thread name and task count. Second, call the .start parenthesis method on the instance. Just like with the function approach, the .start parenthesis method is what triggers the operating system to begin concurrent execution of the thread's .run parenthesis method. 3. The .start parenthesis versus .run parenthesis distinction. It is a critical distinction that you must always call .start parenthesis, not .run parenthesis. Calling .start parenthesis correctly registers the thread with the operating system and invokes .run parenthesis in a separate, concurrent thread. If you mistakenly call .run parenthesis directly, the code will execute, but it will run in the main thread, completely defeating the purpose of multithreading. To summarize, subclassing is the OOP way to create complex threads. Our next lecture 26.06, Thread Using a Class. See you there. Welcome back. In the previous lecture, we extended the threading.thread class. However, sometimes you want to run a method from a class that already exists and cannot inherit from thread. This technique, where you pass an instance method of a normal class as the target to the thread constructor, is a flexible approach. 1. Defining a regular class task. Here we define a simple class, file manager, which does not inherit from threading.thread. It holds data like file name and has a method, process file, which we want to run in a separate thread. This method accepts an argument, mode. This class is decoupled from the threading logic, which is an advantage for clean architecture. 2. Running the method as a thread target. The key step here is creating the thread instance. Instead of passing a standalone function, we pass the instance method, FileManager.ProcessFile, to the target argument. When Python sees this, it correctly binds the method to the object instance. The arguments for the method, in this case, read-only, are passed to the args tuple as usual. When .start parenthesis is called, the process file method is executed concurrently. 3. Advantages of this approach. This method is often preferred because it separates the business logic, which is the file manager class, from the concurrency logic, which is handled by threading.thread. The file manager remains a regular class that can be used in both threaded and non-threaded contexts, making the code more modular and reusable. This is a powerful technique for integrating existing classes into a multi-threaded design. To summarize, you now know 2 ways to create a thread using classes. Our next lecture 26.07, Multithreading in Action. See you there. Welcome back. We have learned how to create individual threads. Now it is time to unleash the full power of concurrency by launching multiple threads to perform different tasks at the same time. This section demonstrates true multi-threaded operation and introduces the essential .join parenthesis method. 1. Defining the concurrent tasks. We define a simple worker function, print numbers, that takes a range and prints the numbers along with the thread's name. We will use this same function as the target for several different threads, each working on its own separate range. The interleaving output will confirm they are running concurrently. 2. Launching multiple threads. We create 3 separate thread objects, named A, B, and C, each targeting print numbers, but with distinct ranges. We store them in a list for easy management. We then loop through the list and call .start parenthesis on each one. Once all 3 are started, they are all running concurrently alongside the main thread, competing for the CPU's time. 3. The importance of thread.joined parenthesis. When the main thread finishes, the entire program exits, even if the worker threads are still running. If the main thread needs the results of the worker threads before continuing, it must wait. The .join parenthesis method forces the calling thread, in this case the main thread, to wait until the thread it is called on completes its execution. We loop again and call .join parenthesis on each worker thread, guaranteeing that the final print statement only executes after all workers are done. To summarize, you can now launch multiple threads and control when they finish using .join parenthesis. Our next lecture 26.08, Using Sleep. See you there. Welcome back. In our previous lecture, we learned that time.sleep parenthesis pauses the execution of a program. In a multi-threaded application, time.sleep parenthesis only pauses the thread that calls it, not the entire process. This is a crucial distinction and a great way to visually demonstrate concurrency. 1. Defining the sleeping task. We modify our worker function to accept a delay argument and use time.sleep parenthesis with that value. When a thread executes this line, it temporarily yields control of the CPU. This pause, however, does not stop the other threads, which remain active and may continue their own execution in the meantime. 2. Observing concurrency with uneven delays. We create 2 threads, worker-A and worker-B, giving them 2 different delay times, 2 seconds and 1 second, respectively. When we start them, both begin their tasks. However, when they reach the time.sleep parenthesis call, worker-B will finish its pause and print finish sleeping 1 second before worker-A, which is still waiting. This clearly illustrates that the threads operate independently. 3. The concurrency challenge. While this is great for allowing threads to perform background tasks without blocking the main thread, it highlights the lack of control over execution order. If both threads were accessing and modifying the same shared resource like a variable or a list, the unpredictable order caused by these natural or artificial delays like time.sleep parenthesis would quickly lead to race conditions and corrupted data. This challenge leads us directly into our next set of topics. To summarize, time.sleep parenthesis is thread-specific. Our next lecture 26.09, the ticket booking use case. See you there. Welcome back. In this lecture, we tackle a classic multithreading problem that demonstrates why uncontrolled concurrency can be disastrous. The ticket booking use case. We will simulate 2 users simultaneously trying to book the last available ticket. 1. The shared resource and task. We define a global variable, available ticket, and initialize it to 1, representing the last ticket. Our book ticket function represents a user trying to book. The critical part of this transaction involves two sequential steps. First, checking if tickets are available, and second, decrementing the count if they are. The problem arises if two threads execute the first step before either one can execute the second. 2. Creating the race condition. Inside the if condition, we simulate a small delay using time.sleep parenthesis. This pause is the key. While the first thread, say, user1, pauses after checking that available tickets is greater than 0, the operating system may switch execution to the second thread, user2. User2 also sees that the ticket count is 1, enters the if block, and pauses. When both threads eventually finish their pauses, they both successfully decrement the ticket count, resulting in a negative number which is logically impossible. This is known as a race condition. 3. Launching the competing threads. We launch two threads, user-1 and user-2, and then wait for them to finish with .join parenthesis. When you run this code, you may consistently see an incorrect final ticket count, likely -1, even though only one ticket was available. This severe bug in shared data integrity is precisely why we need the next topic, thread synchronization. To summarize, the ticket booking problem proves that sharing data between threads without strict control is unsafe. Our next lecture 26.10, Thread Synchronization. See you there. Welcome back. The ticket booking use case exposed a severe problem, the race condition, where multiple threads corrupt shared data. The solution is thread synchronization, which means coordinating the execution of multiple threads to ensure that when one thread is accessing a critical piece of data, no other thread may interfere. 1. The critical section. A critical section is any part of the code where shared resources, like variables or data structures, are accessed or modified. In the ticket use case, the critical section was the if block where we checked the ticket count and then decrement it. To prevent race conditions, we must ensure that only one thread can be inside this critical section at any given moment. This is called mutual exclusion. 2. Introducing the lock object. We have a simple synchronization primitive is the lock object from the threading module. A lock starts in an unlocked state. When a thread wants to enter a critical section, it calls lock.acquire parenthesis. If the lock is unlocked, the thread immediately enters and the lock becomes locked. If the lock is already locked by another thread, the calling thread is forced to wait until the lock is released. 3. Using the lock manually. The pattern for using a lock involves three parts. First, call lock.acquire parenthesis before the critical section. Second, execute the critical code. Third, call lock.release parenthesis after the critical code. It is a practice to wrap the critical section in a finally block. The finally block ensures that lock.release parenthesis is always called, even if an exception occurs inside the critical section, preventing a potential deadlock. To summarize, locks prevent race conditions by forcing threads to wait their turn. Our next lecture 26.11, Add More Logic. See you there. Welcome back. We are now going to fix the critical bug in our ticket booking use case. The negative ticket count was caused by both threads entering the critical section simultaneously. We will now integrate the lock object to ensure that only one thread can check and modify the available tickets variable at a time. 1. Initializing the lock. Just as available tickets is a shared resource, the ticket lock must also be created once and shared among all threads that need to access that resource. We create one instance of threading.lock parenthesis at the global level, and this single lock instance will now be used by both of our competing threads. 2. Protecting the critical section. We insert TicketLock.acquire parenthesis at the entry of the critical section. Now, when user 1 calls this, it acquires the lock and proceeds. When user 2 calls it immediately afterward, it finds the lock held and is forced to wait indefinitely at this line until the lock is released. This enforces mutual exclusion. We ensure TicketLock.release parenthesis is called an A finally block to prevent a deadlock if an error occurs within the protected code. 3. Verifying the fixed logic. When you run the synchronized code, you will observe the output confirming that one thread acquires the lock first. The other thread is seen waiting. The first thread successfully books the ticket and decrements the count to 0. When the second thread finally acquires the lock, it finds that available tickets is no longer greater than 0, and it is correctly denied the ticket. The final ticket count is consistently 0, confirming that our race condition has been successfully fixed. To summarize, locks are the foundation of safe multithreading. Our next lecture 26.12, Synchronization using lock. See you there. Welcome back. In the previous lecture, we successfully used lock.acquire parenthesis and lock.release parenthesis to solve the race condition. However, using a try finally block for every critical section can be repetitive. Fortunately, Python's lock object is also a context manager, offering a cleaner and safer syntax. 1. The context manager pattern. A context manager is an object that defines the runtime context for a block of code, automatically handling resource setup and teardown. You have seen this with file handling, with open parenthesis file, name comma mode parenthesis as f colon. For a lock, the with statement automatically calls .acquire parenthesis upon entering the block and guarantees that release parenthesis is called upon exiting the block, even if an error occurs. This eliminates the need for manual try. Finally, 2. Refactoring the booking logic with look at how cleaner the code becomes. We simply use with ticket lock colon to wrap the critical section. The lock is acquired when execution enters the with block and automatically released when execution leaves the block, whether it exits normally or due to an exception. This is the recommended way to use locks in Python for mutual exclusion. 3. The advantage of clean code. The primary advantages of using the with statement are simplicity and safety. It prevents accidental deadlocks caused by forgetting to call .release parenthesis, as Python guarantees the release mechanism. This leads to code that is not only shorter but is also more robust and easier for other developers to read and understand. To summarize, use the with statement for all critical sections protected by a lock. Our next lecture 26.13, Synchronization using semaphore. See you there. Welcome back. While the lock object enforces strict mutual exclusion, allowing only one thread at a time, there are scenarios where you need to allow a specific, limited number of threads to access a resource concurrently. For this, we use the semaphore. 1. What is a semaphore? A semaphore is a synchronization primitive that maintains a counter. This counter is initialized to a specific value, representing the number of available permits. When a thread calls .acquire parenthesis, the counter is decrement. If the counter is greater than 0, the thread proceeds. If the counter is 0, the thread blocks until another thread calls .release parenthesis, incrementing the counter and freeing a permit. 2. Initialization and usage. We initialize the semaphore with 3, meaning only 3 threads can enter the database connection critical section at any one time. We use the convenient with statement just like with a lock. Threads will execute the connect to db function. The first 3 will proceed immediately, but the 4th thread will be blocked at the with statement until one of the first 3 threads calls .release parenthesis by exiting the block. 3. Running the semaphore simulation. We launch 5 threads to simulate 5 clients trying to connect to a database that only allows 3 simultaneous connections. You will observe that 3 threads acquire the connection immediately, while the remaining 2 are forced to wait for 2 seconds. As soon as one of the active threads finishes its work and releases its permit, one of the waiting threads immediately grabs it and continues. The final output confirms that only 3 threads were active at any given moment, successfully managing the limited resource. To summarize, locks are for mutual exclusion, semaphores are for boundary control. We have learned synchronization. Our next lecture 26.14, Thread Communication. See you there. Welcome back. We have successfully synchronized threads to protect shared data. The next critical topic is thread communication. How do we enable one thread to inform another thread about a change in state, a completion of a task, or that new data is available? 1. Why communicate? Synchronization prevents simultaneous access, but it doesn't help threads coordinate their actions. For instance, an uploader thread needs to tell a processor thread when a large file is ready, or a main thread might need to signal an indefinitely running worker thread to shut down. Coordination between tasks is the essence of effective multithreading. 2. Using a shared boolean flag. The most basic form of communication is a shared variable, typically a boolean, used as a flag. One thread, the main control thread, sets the shutdown flag to true to signal a state change. The worker thread continuously checks this flag inside its main processing loop. This constant checking is called polling. 3. The downside of polling. While simple, polling is inefficient. The worker thread spends valuable CPU cycles repeatedly checking the shared flag, even when the flag hasn't changed. If the task is long, the shutdown will be delayed until the task finishes. If the check is too frequent, it wastes resources. If it is too infrequent, the thread responds slowly to the signal. To summarize, Boolean flags are easy, but polling is inefficient. Our next lecture 26.15, Using a Boolean flag. See you there. Welcome back. We established that using a shared Boolean flag with polling is the simplest method for inter-thread communication. In this lecture, we will implement this pattern to control the shutdown of a long-running worker thread from the main thread. 1. Defining the flag and the worker task. We define stop_flag and, importantly, a flag lock. Even for a simple boolean, it is best practice to protect it with a lock to avoid race conditions if two threads try to modify it simultaneously. The worker task runs an infinite while true loop. In each iteration, it acquires the lock, checks the flag, and breaks the loop if the flag is set. Then, it releases the lock and executes its simulated work for half a second. 2. The signaling mechanism. We define a separate function, signalStop, which runs in its own thread. After a 2-second delay, this signaling thread acquires the lock, sets the stop_flag to true, and releases the lock. The next time the worker task thread checks the flag, it will see the change, exit its loop, and terminate gracefully. 3. Launching and observing shutdown. We launch both the worker and the signaler threads, and the main thread waits for both to complete using .join parenthesis. The output will show the worker processing for about 2 seconds before the signaler sets the flag. Immediately after the signaler sets the flag, the worker's next check causes it to break its loop and exit. This confirms successful controlled communication. To summarize, the Boolean flag works, but the polling wastes CPU resources. Our next lecture 26.16. Run and summarize. See you there. Welcome back. We just implemented a thread shutdown mechanism using a Boolean flag. Let us now run this code, observe the exact behavior you may see, and critically analyze the efficiency of this polling approach. 1. Execution review with correct output. When we run the script, we see the worker thread start immediately and print working. The signaler thread prints its intent to wait 2 seconds. The worker continues printing working several times while the signaler is delayed. This concurrent activity is expected. Once the signaler sets the flag, the worker's next check causes it to break its loop and terminate. Functionally, the shutdown is successful and controlled. 2. The problem polling, also known as busy waiting. Although the worker thread uses time.sleep parenthesis to simulate work, it is still consuming CPU time on every half-second iteration just to check the flag. If the worker's task was short, say a few milliseconds, it would be checking the flag thousands of times per second. Polling is like constantly looking at your clock while waiting for the next minute to start. It is an inefficient use of resources because the thread is active but not performing meaningful work until the flag changes. 3. The solution, event-driven communication. The goal should be for the waiting thread to consume 0 CPU resources until the event happens. Instead of polling, we use a mechanism where the thread can explicitly go to sleep and be woken up only when another thread signals the event. This is the wait and notify pattern, which maybe we will see next. To summarize, we must transition from busy waiting to blocking communication. Our next lecture 26.17. Thread communication using wait and notify. See you there. Welcome back. We have seen that polling causes busy waiting, which wastes CPU cycles. To solve this, we need a way for threads to sleep when they have nothing to do and wake up only when necessary. Python provides the condition object for exactly this purpose. 1. The condition object. A condition variable is always associated with a lock. When you create a threading.condition parenthesis object, it creates a lock internally. This object allows one or more threads to wait until they are notified by another thread. It serves as both a synchronization primitive like a lock and a communication channel. 2. The wait method. This is the consumer side. When a thread calls condition.wait parenthesis, three things happen atomically. First, it releases the underlying lock. Second, it blocks execution and goes to sleep, consuming no CPU. Third, when it is eventually woken up, it automatically reacquires the lock before continuing. This is much more efficient than polling. 3. The notify method. This is the producer side. When a thread has performed a task or changed a state that the waiting thread cares about, it calls condition.notify parenthesis. This sends a signal to wake up one of the threads waiting on this condition. Note that notify does not release the lock immediately. The notifying thread must exit with block or explicitly release the lock before the woken thread can proceed. To summarize, use wait to sleep and notify to wake up. This is the standard pattern for efficient thread communication. Our next lecture 26.18. Use wait and notify. See you there. Welcome back. We are now upgrading our thread communication mechanism. We will replace the inefficient polling method with the elegant and CPU-friendly wait and notify mechanism using the condition object. 1. Set up the shared condition. We define a new boolean flag, data_ready, and, crucially, a shared threading.condition parenthesis object. The condition object inherently contains its own lock, which we will acquire using the with statement before accessing the shared data_ready flag. 2. The waiting consumer thread. The consumer task acquires the condition's lock. It then uses a while loop to check the state of data_ready. Since it starts as false, the consumer calls condition.wait parenthesis. The consumer thread immediately releases the lock and goes into a blocked state, consuming no CPU. It will remain asleep until another thread calls .notify parenthesis. 3. The notifying producer thread. The producer task runs for 3 seconds. Once ready, it enters the critical section using the with condition : block. It sets data_ready to true and then calls condition.notify parenthesis. This wakes up the waiting consumer thread. The consumer then waits for the producer to exit the with block and release the lock before it can reacquire the lock and continue its execution. To summarize, the wait and notify mechanism is far superior to polling. Our next lecture 26.19. Queues and thread communication. See you there. Welcome back. We have seen how to synchronize shared variables with locks and coordinate threads with wait and notify. However, the most robust Pythonic way to handle both synchronization and communication is by using the queue data structure. 1. Why use queues? Thread communication often involves passing data, not just signals. Queues combine data transfer with blocking synchronization. In essence, when a thread puts an item into a queue, it automatically notifies any waiting threads. When a thread tries to get an item from an empty queue, it automatically waits until an item is available. This makes the queue module a perfect, all-in-one solution for multithreading coordination. 2. Thread safety and FIFO. The queue.queue object is explicitly designed to be thread safe. It uses internal locks and condition variables to manage access, meaning you never need to manually apply a lock when using its methods. A standard queue follows the first in, first out, or FIFO principle. The first item put into the queue is the first item that comes out. 3. The primary methods. To add data, we use .put parenthesis. To retrieve data, we use .get parenthesis. By default, both methods are blocking, which is the key to efficiency. If a thread calls .get parenthesis on an empty queue, it blocks and sleeps until another thread calls put parenthesis. Similarly, if you define a limited size queue, .put parenthesis will block if the queue is full. This elegantly handles the wait and notify communication necessary for passing data. To summarize, queues simplify complex synchronization and communication needs. Our next lecture 26.20, Producer-Consumer Pattern. See you there. Welcome back. The producer-consumer pattern is a powerful model in multithreading. It uses a shared queue to decouple the task generator, the producer, from the task executor, the consumer. 1. Defining the shared queue. We start by creating a shared work_queue instance from the queue module. We set a max size of 5 to create a bounded buffer. This means the producer thread will automatically block if it tries to put an item into a queue that already contains 5 items. This is a built-in synchronization control. 2. The producer thread using .put parenthesis. The producer generates items, in this case, task number 1 through 10, and calls work_queue.put parenthesis. Since the queue is thread safe, we don't need locks. Notice the critical last step, putting a special value, none, into the queue. This is a common way to signal to the consumer that no more tasks will be produced, allowing the consumer to shut down gracefully. 3. The consumer thread using .get parenthesis. The consumer runs an infinite loop and calls work_queue.get parenthesis. This call automatically blocks and sleeps if the queue is empty, efficiently eliminating polling. The consumer processes the item and then, if it receives the none signal, it breaks the loop but also puts none back into the queue to signal any other waiting consumers, ensuring a cascade shutdown. To summarize, the queue is the primary tool for clean data exchange between threads. Our next lecture 26.21, 3 types of queues. See you there. Welcome back. We've established that the queue is the ultimate tool for inter-thread communication. While we used the default queue in the producer-consumer pattern, the queue module provides 3 different classes based on how tasks should be ordered. 1. Standard queue using the queue class. This is the default and most common type we used. It implements the FIFO principle, first in, first out. Tasks are processed in the exact order they were submitted. You use this when the order of arrival is important, such as processing user requests or logs in sequential order. 2. LIFO queue using the LIFO queue class. This implements the LIFO principle, last in, first out. This structure behaves like a stack. The last item added to the queue is the first one retrieved by the consumer. You may use this in scenarios where you want the latest changes or revisions to be processed immediately, like in an undo history stack or processing newer requests first. 3. Priority queue using the priority queue class. This type processes items based on their assigned priority, regardless of when they were added. When using this queue, the items must be tuples where the first element is the priority number. The lowest number means the highest priority. You would use this for mission-critical applications where error reporting must happen before processing standard tasks, or when managing different service tiers. To summarize, these queues give you flexibility in how you manage tasks in a concurrent environment. Our next lecture 26.22, Types of Queues. See you there. Welcome back for the final lecture on threads. We have covered the 3 main thread-safe queue types. Now, let us summarize them in a handy comparison table to help you choose the right tool for your specific concurrency needs. 1. Queue comparison table. This table summarizes the key characteristics of the 3 queue types. The standard queue uses FIFO, where the item that went in first is the item that comes out first, ideal for processing tasks in order. The LIFO queue uses LIFO, which retrieves the newest item first. Finally, the priority queue retrieves items based on the priority value assigned to them, with the lowest number signifying the highest priority. Two. Conclusion threading. Congratulations! You have completed the section on threads. We started with the basics of thread creation, understood the critical need for synchronization using locks and semaphores to protect shared data, and finally mastered communication using the wait and notify pattern and the highly effective thread-safe queues. These are the fundamental tools for building robust, high-performance concurrent applications in Python. Looking ahead, networking. Now that we know how to run tasks concurrently, we will move to our next major topic, networking. We will learn how to make our programs communicate with the outside world, covering everything from simple HTTP requests to building our own custom network servers using sockets. This opens up entirely new possibilities for your applications. We will begin section 27 by exploring the basics of retrieving data from the internet, starting with downloading a simple HTML page. Join me in lecture 27.01. Introduction. See you there.